In this lecture, we'll be continuing the discussion on the rupture of thin films. Now, by thin film, we mean a thin film where the mean thickness H0 is much larger than the horizontal extent. And we had defined a parameter epsilon, which was H0 by L. And we said that when this parameter epsilon is much smaller than 1, we had expanded the primary variables, that is the velocities and the pressure, as a function, as a perturbation expansion in epsilon. And we collected the leading order terms, meaning terms which are order 1 terms in epsilon. And these equations were highly simplified. That's where we stopped in the previous lecture. Now, these equations that we derived contain the variable height h of x comma t. So what we want to do in this lecture is to derive an equation for the thickness of this, evolution equation for the thickness of the interface as a function of space and time. To do this, I'll first summarize the equation that we had already derived. So these are the continuity and the x and y momentum equations. Then we have the boundary conditions both at y equal to 0 and the interface conditions at y equals h of x comma t, which is the kinematic condition, the normal stress balance and the tangential stress balance condition. For convenience, I've labeled these equations or from A through G. So notice that some of these equations are quite straightforward. For example, I can integrate equation C to get the hydrostatic pressure variation across the thin film in the y direction. Now, once I know that pressure, I can use the equation B, which is the x momentum equation, to get the velocity u0, the horizontal velocity u0. I can use the continuity equation to get the vertical velocity v0. And then we can use the velocities u0 and v0 and substitute them into the kinematic condition. And that's how we would get the equation for the evolution equation for the height. Now, of course, when we do these integrations, we get integration constants, and we'll have to use the boundary conditions both at the wall and at the free surface to get to know the value of these constants. So let's start by basically getting equation C. So let's start by integrating equation C. That's the pressure equation, the hydrostatic pressure equation. So let me write that down. So the equation that we have is there on the screen. So we have P0 will be minus epsilon cube L square by nu u0 times G plus times y plus an integration constant C1. But since this is a partial derivative with respect to y, when I'm doing an integration, I'm doing an integration with y. So I have an integration constant which can be a function of x and t. Right? Now I can use this pressure into the normal stress balance, that is equation F, to get the constant C1. The unknown function C1, remember it's a constant of integration as far as y is concerned, but it's a function of x and t. This function can be determined from the normal stress balance. That's equation F. So let's substitute this pressure into equation F. But remember, this condition, the normal stress balance condition, is valid at y equals h of x comma t. So I may sometimes avoid writing h of x comma t all the time and simply write it as variable h. So it's understood that this h is a function of x and t. So let's start by doing this. So we have minus epsilon cube L square. I will replace the kinematic condition, kinematic viscosity nu. I'll write it in terms of dynamic viscosity. So I know that nu equals mu by rho. So I have rho g by mu u naught times this is at y equals h plus c1 of x comma t minus p infinity. This is the left hand side of equation f. This is minus epsilon cube ca hxx, right? So now I have c1 of x comma t will be p infinity plus mu naught times h this is my the constant c1, right? Now once I know this constant c1, I can substitute it back into my expression for pressure to get P infinity Q naught times y minus h we'll label this as h, right? Now a few checks that we can do. For example, if there is no curvature, then you can also verify that at y equals h, the second term on the right hand side of equation h disappears, and what we now have is P becomes P infinity. That's because there's no curvature. And you can also verify that at y equals 0, again for an interface without curvature, the pressure is more than the atmospheric pressure P infinity. By how much value? It's exactly it's more by a factor of epsilon cube L square rho g by mu u naught. The reason for that is because as you go down, the pressure increases, right? Now if this pressure P infinity is known, if we know this pressure, then we know the pressure distribution in the thin film. Okay. Also notice that P0 linearly varies with the height variable y. Okay. So what does it tell you? That if I take the derivative with respect to x, okay, then I have epsilon cube L square rho g by mu u naught times hx minus epsilon cube ca hxxx. Okay, so I've got the pressure gradient del p by del x, del p0 by del x. The reason I need this variable is because del p0 by del x appears in the x momentum equation. I can now integrate the x momentum equation, that is equation B. Equation B, we get del u by del y will be integral of the pressure gradient dy. Right? Now, when I have this, I have this can just simply be written as del p by del x of y plus some constant C2. The reason for this is if you notice the expression that I have del p0 by del x, it does not depend on the variable y at all. So therefore it comes out of the integration and I just have integral of dy just becomes y. I have a constant C2, right? And if I go integrate it further, I have del p0 by del x becomes that u0 becomes del p0 by del x, y square by 2 plus c2y plus c3. Okay, this c2 is c2 of x and t, c3 is c3 of x and t. In general, these are functions of x and t because I'm doing an integration in y. Okay, so this kind of a straightforward integration was possible because this equation, this relationship del p by del x is not a function of y. Okay, so now I've got the velocity in terms of two additional constants C2 and C3. Now we will first use this. We will use the no slip condition and at the wall y equal to 0. So that's equation D. U of 0 is equal to 0 at y equal to 0. And the state of equal tells me C3 of x comma t is identically 0. Okay. And if I use the tangential stress condition, that's the tangential stress condition is equation G. We have del u0 by del y equal to 0 at y equals h. And this essentially means del p0 by del x times y plus c2 is equal to 0 plus c2 is equal to 0 at y equals h implies c2 of x comma t will be minus del p0 by del x times h. That's the expression for C2, right? And now that I know C2, I can substitute it back into the velocity field expression that I have. Therefore, I have the velocity essentially becomes del p0 by del x times y square over 2 minus h times y. That's my velocity field. So let's label this as well. So let's call this equation I. Okay. So notice that the velocity field is a parabolic profile. So if this is my thin film, so if I have an undulation like this, so the velocity at any point will be a parabolic profile. Of course, this is an exaggerated view, but where the thickness is less, the velocities are higher, and where the thickness is more, the velocity is of a lesser magnitude because it's extending over a larger height. That's my velocity profile. Okay. Now we still haven't used the continuity equation. That's equation A. Okay. And we have not used the boundary conditions. We have not used the no penetration condition D. We have also not used the normal stress balance. That's equation E, right? So let's use them. Integrating equation A That's the continuity equation. I'm going to integrate from 0 to h. I have del by del x of u0 dy. The second term essentially simply becomes y0. But since I have the no penetration condition at the bottom, this simply just reduces to y equals h is equal to 0. Right? Therefore, I get an expression for velocity at the interface. Okay, in terms of an integral over the variation of u with respect to x. Okay, now using equation E. And what is equation E for us? Equation E is the kinematic condition, right? So the kinematic condition says that, let me just show this again here. The kinematic condition essentially says V0 is del h by del t plus u0 del h by del x, right? So I have V here, so I can substitute for V in terms of so I have minus 0 to h del u0 by del x dy. This is the V0 at the interface. This will be del h by del t plus u0 del h by del x. Remember this u0 that we have to take, this should be taken at y equals h, right? So I can bring all of them to one side. I have integral 0 to h del by del x of u0 dy plus dh by dt plus del h by del x. This is equal to 0, right? Now we want to use the velocity u0, but before we do this, let's quickly use the Lebnet's rule. So what's the Lebnet's rule? Lebnet's rule allows me to change the order of the integration and the derivative. So how do we have? Let's say we have an arbitrary integration. Let's say going from a to b, and it's an integration with respect to some dummy variable s, some function d of s comma t. Let's just do ds. This essentially becomes d by ds, the total derivative, going from a to b, f of s ds. Right? So make a small correction to this. So Lebnet's rule says if I have a function, if I am integrating from a to b of a function of two variables s and t, I'm taking a partial derivative with respect to s, integration with respect to t, then I can bring this derivative out, d by ds. I can now do an integration first of this function with respect to time and then take the derivative. Okay. Let's apply this to the function that we have. What's the function we have? We have an integral of this form, del u0 by del x dy, right? This can now be written as d by dx 0 to h u0 of dy. Okay. So this essentially becomes d by dx of integral 0 to h. We already know the expression for u0. What's the expression for u0? It is del p0 by del x of y square over 2 minus hy. That's the expression for u0. And then that's my derivative, all the terms in this expression. So we can do a simplification here. So I can do a derivative straight away, because if you notice here, del p0 by del x is a function of x alone. So if I do this, I have 0 to h del square p0 by del x square of y square over 2 minus hy, okay, minus del p0 by del x minus hx times y, right? And this whole thing I have to integrate it with respect to y. And I will leave it to you to do the integration. It's a straightforward integration. Del square p0 by del x square can come out. I have y square over 2. Integral, essentially y square becomes y cube over 3. And I have to substitute, the integral is from 0 to h. So I have to do the same thing for the other terms. And what do I get? I get del square p0 by del x square. The first term becomes h cube over 3 multiplied by 2, that's 6, minus h cube over 2. Then I have minus del p0 by del x. I have minus hx, and the derivative of y essentially becomes h square over 2. That's my expression that I have here. So this, remember, is my del u0 by del x dy, right? Now, before I wrote down this Lebnet's rule, we were writing down this expression here. I was writing down this equation. So now we have got the first term of this equation, that is 0 to h del u0 by del x of dy. Now I can substitute this into this. I have already got this expression here in terms of pressure and pressure gradient and height. So if I take it from here, these are related, and so now simply gives me, substituting 0 to h del u0 by del x dy in the kinematic condition. We have, so del square p0 by del x square. So I have h cube over 6 and I have h cube over 2. So this essentially becomes minus h cube over 3, right? The next term essentially becomes del p0 by del x times minus hx times h square over 2. Then I have the two terms in the kinematic condition, that is time derivative with respect to t, and then I have velocity u0 times del h by del h. So u0 can also be written in terms of the pressure, that's del p by del x times h square over 2 minus hy. This is my u0 at y equals h times hx. Okay. Now I want an evolution equation for h in terms of t. So I can pull this out. I have del h by del t. Essentially, we can do some simplification, and we get the first term would be del square P0 by del x cube, del x square times h cube over 3. Now we can make some simplifications here. If I apply, I have del P0 by del terms here, couple of terms here, and some cancellations will happen, and I have del P0 by del x times h square over 2 times hx. Okay. This, remember, here I have not applied the condition. This has to be at y equals h. Okay. So if I apply this at y equals h, we have these cancellations and some of the simplifications. And so finally what we have is this right hand side can be combined into one single term that becomes del by del x of h cube over 3 del P0 by del x. This is my evolution equation, right? So let me explain what this is. This is evolution equation for h of x comma t in terms of the pressure gradient P0, right? Now, have we already got this expression P0? The answer is yes, we've already got this expression P0. Note that pressure P0 is given by equation H. What is this? P0 essentially becomes P infinity minus epsilon cube L square rho g by mu u naught hy, h minus y minus epsilon cube gamma by mu u naught hxx. This is my expression for the pressure. So what we have managed to do in this analysis is to derive a simple evolution equation for the height. You can clearly see it's a partial differential equation because h is a function of two variables, x and t. Once we specify the pressure gradient P0 as a function of x, we automatically we can substitute this pressure gradient into this equation, and we have a simple elegant expression for the evolution of the height. The height will evolve as per this equation. So the last variable that the label that we had used was equation I. So let's call this equation as equation J. Okay. Now there are several steps that we can go forward from here. For example, the expression for pressure that is written down here at the bottom, this expression for pressure does not have a driver of a rupture mechanism. So in the next lecture, what we're going to do is we're going to introduce the so-called disjoining pressure. And the evolution equation J does not vary. That's the beauty of this equation. The evolution equation J does not vary, but all that we need to do is we can add additional physics into this pressure term, and then we can see how does the evolution of the interface change because of new physics that we have added to. Okay, so I'll stop here, and then we will look at the effect of van der Waals forces in the next lecture. Thank you.